This information is brought to you by Charles Sturt University.
So, mostly for the people that are wanting to do recording, this is the bit that cut off yesterday. Just want to repeat my last few things as yesterday. This was looking at a shortest path algorithm. I can't remember how to pronounce it. I actually never know how to pronounce it.
The
Discourse algorithm. There it is. So path, it's by finding the shortest path, essentially. So it's basically looking at colouring in the nodes and that you've already visited. That's what the colouring is about. So you can just, in practice, you normally just have a list of visited nodes, etc. And at each point in time, you're always trying to work out from all the nodes. You just pick the node that's next closest to what you've already visited. So at any point in time, so you've already got a few things coloured like here. You go to the one that's closest. So out of the two left, the numbers on them represent the shortest distance we know so far from our source point. So far F has got the distance of 8, so far D is the distance of 9. So the closest one of what we so far is F, so that's the one we'll look at next. So it's a greedy algorithm. So you visit F next at any point in time, and once you visit that node, then you just go, look, well, let's just check if all the distances I've got on all the other nodes are still actually the shortest. Maybe going by F is actually a shorter path after all, and therefore I can reduce everything down. And that's what you do. So you go for F, look at all the boats you haven't visited yet, so just D. I know it's up 8 to F directly. If I do another length 2 on here, I can get it by F, I can get a distance of 10. Is that better than what I had before? No. I think the answer is no. I don't update the distance on D at all. And therefore, I don't do anything. But if it was shorter, you go, oh, fantastic, I actually found a shorter path. I can reduce the numbers at any point in time. So when a node isn't visited yet, so when it's black, these numbers represent the shortest distance we know so far, but as you're going through, they might come down because you might find a better path. So in this example, as you're going around, so the distance from B to E is 6, but you go from B to A to C to E is actually a shorter path. And as you colour more nodes in, you can see that number drops from 6 to 5 at some point in time as you find the shorter path. And the algorithm stops in one of two ways. It either stops when you finally visit the node you're trying to get the distance to. So we were trying to find the distance from B to D. So as soon as you colour that node in, so as soon as you visit it, that means that's it. You know what the shortest distance is and you can stop. That's the desirable finish. The other way it finishes is when, at any point in time, you're trying to find the next node to visit, and so you're just looking for the node with the shortest distance so far. If when you're doing that, the only nodes available have infinite distance on them, that basically means you cannot reach them at all from anything you've got. And as soon as you get to that point in time, you know that there is no shortest distance, you just can't reach what you're going for, and you can exit at that point in time. So that would happen in a disconnected graph, if you're going to reach it. And again, so if you're doing it by hand, which is what we're going to do, you can see a disconnected graph pretty quickly. You go, oh, I know I can't reach it. But for a computer algorithm, computer algorithm is just looking at just tracing edges one at a time, so I can't see that straight away necessarily. So that was the last example of weighted graphs. So that's the end of the graph theory topics. And so what we looked at graphs and some special types of those. So directed ones, looked at trees, and looked at weighted graphs, and looked at various algorithms, understanding of those sort of things. And it gives a good introduction to things like data structures, thinking about that sort of stuff, which we'll do more of in a second. And they're useful topics, just useful ways of trying to understand data. Your assignment 3 is on that topic. And so you can do assignment 3 this weekend, for example, if you want to. We'll do some more practice questions in the tutorial today. So that's a good thing to look at. Okay, so there's heaps of terms that come with graph theory, and there's lots of them there. Instead of reading them all out to you, I've updated the formula sheet about a month ago, which had all these terms just listed like that, but I've given some definitions for some of them on that, so you might find that useful to download again, because you need to know what they mean. So I could ask in your exam, is this graph complete? You need to know what that means, and be able to evaluate if it is or not, etc. So it's useful to have lots of terms, and there's quite a lot of them, as you can see. You need to know all the characteristic, how to work it out, and for a planar graph it's equal to 2, that sort of definition. And then how you need to know about how, if you can traverse a graph or not, which is about following Euler paths or circuits. And then we did quite a few algorithms towards the end there. So adding to a binary search tree, finding the maximal flow, which is Ford-Volkerson's algorithm, finding the minimal spanning tree, which is Prim's or Kruskal's, and the shortest distance, which is the one I can't pronounce. So there's some algorithms, and you need to know those. I jotted some notes down on the example formula sheet that may be completely may not be sufficient for you at all to understand what's happening. So if you want to have some tips when you're going to your exam what to do, maybe you need to customise that formula sheet. And as you try your assignment, if you do some of those algorithms, you might just go, I just don't like how Michael's written it down, I'll do it my own way. And they're quite common, well-known algorithms. So you go, I don't like this how it's written, look it up, see how other people describe it. So I describe District's algorithm by using colour in blue, that's just visiting nodes. Other people won't describe it in the same terms. Maybe that's easier for you to understand. So in the tutorials and in the online meeting, I'll show a different way for the maximal flow problem, just how to write it down, which people might prefer, or maybe not. But just give you some variety. But what I want to do next is the next topic, which is looking at the ideas of algorithms. So we've touched on algorithms already, and that's what we've just been talking really. But just trying a way of trying to understand algorithms is sort of what we're looking at the next sort of topic. So what we're going to do is talk about algorithms, just give a sense of how to work out if a good algorithm's good or not, how you should do that. And then that sort of arises the idea of looking at recursion in particular, and how to count the complexity of recursive functions. And so the first bit is very much a computer science aspect. Towards the end, which is looking at recursive relations, etc., is very much more maths. And that has applications not just in terms of computers by any means, but in terms of sort of population growth, etc. So, but we won't do it all today, so just start with algorithms. Can you give some examples of algorithms that we've done in the subject, or just in any algorithm at all?
Depends on your definition of an algorithm.
It does. What's the definition of algorithm is the next question. But examples are sometimes easier than trying to define it. If you get some,
in programming, algorithm is just a way to solve a problem.
Okay, way to solve a problem. So what's some problems we've been trying to solve? Yesterday, what's some problems we're trying to solve?
Shortest path.
Okay, so shortest path. So it's an algorithm to find the shortest path. So it's basically some sort of bunch of steps or recipe, or whatever you want to call it, to try to do it. So we looked at shortest path. What other sort of problem types we looked at?
Maximal flow.
So maximal flow, yep. So it was minimal spanning tree. And you can see for minimal spanning tree there was 2 different recipes, 2 different algorithms that I mentioned to how to do it. And so when you have a certain problem type, there isn't necessarily one algorithm to do it. There can be lots. There can be lots of good ones, even. How can you tell them apart? So questions that will arise is, which is better, Prim's algorithm or Kruskal's algorithm? Which one's better? Now, for us doing it by hand, it doesn't make much difference. But if you're trying to compile it to a computer, one is better than the other in certain contexts. does depend on the number of vertices and edges you've got. So we've done other ones, like when we did combining numbers in different bases. We looked at multiplication, division, subtraction, addition, etc. And so the way you did algorithms back in primary school was you did column addition, for example. That's an algorithm. That's the process of adding two big numbers together. So what is an algorithm? People don't quite agree with the definition, but basically it's a sort of a recipe, a procedure to do some sort of task. Some things which I think are useful is it needs to be a finite set of precise instructions. So finite's the key word there. And they need to be easily understood, etc. You need to require the procedure to finish in a finite amount of time and to use a finite amount of space, or memory, I guess is how we think about it. So people came up with trying to nut idea about algorithms before computers existed. So they were talking about this before we had, we know about computers. So it predates it. But essentially, their arguments about what an algorithm is pretty much is it's a computer program. It's pretty much what the decision pretty much in the end of the day is. And so you can see that a good algorithm really requires finite amount of memory, actually finishes in a finite amount of time, and the program itself is just a finite number of lines of code. So all nice real world constraints essentially.
Does order matter? Order, like of the instructions?
If you change the order of instructions, what do you reckon will happen?
We change everything else.
You change your algorithm essentially.
Why is it a step? Why is it a finite step?
So
Order matters.
okay. Finite tuple then, if you want to use different. So often you think of algorithms as having an input and an output, and I think that's a good way of thinking about it. Is that compulsory?
You don't need an output.
Could be a void.
You don't need an input.
Let's look at this. This is just a snippet of code snippet here. Now, not everyone. I mean, you guys are all know enough programming, I presume, to understand it, but certainly not everyone on the recording does. Can someone explain what that's doing? It's pseudocode. It really isn't an actual code as you work out quickly.
It loops starting at 2, continuously incrementing by 1.
Yep.
And it'll break if the sum of each digit to the power of 4 is equal to the loop index.
Equal to the number itself. So what it's doing is it's just the problem it's trying to solve is it's trying to find a number that if you get each digit take to the power of 4, it equals to the number itself. Does it have an input? No, not at all. Does it have an output?
Not as of yet, no.
Well, essentially,
Really, you know when it will happen. You know when it will happen. It'll break. Well, I guess it will.
So here's a question for you.
Exactly.
If you type program that code properly, like you can see that S equals line is pseudocode, certainly not a real language, not real computer code.
You could just not have.
So there's two options for it. Would it ever break? It's an infinite loop, potentially.
Probably at some point.
Do we know?
No, because S is just growing exponentially, whereas I is just going up by 1, like you're never going to reach it.
So it's actually unclear what's going to happen in this algorithm to us. It could go either way. So the output is two options. It'll either break and terminate quite cleanly, or it will go an infinite loop. In practice, that might mean there's an overflow in I, which the program might catch and just crash on you, which is a good thing. So crashing would at least would not, or if worst case scenario actually does loop forever.
That makes more RAM.
and
No.
and in a computer,
Yeah.
so it would probably just overflow and just start basically restart the loop. So it's going to begin. Very good. But so the output really in this program is if it terminates correctly or crashes. Even that is an output, if you want to think of it that way. So all algorithms give you some output, even if it's just really simple lines of it crashes or doesn't crash. And that's in the information. Incidentally, that program would finish with 1634. That was what it would be terminating. So it actually does terminate, but it isn't clear. And so that's why writing a program which checks for infinite loops is harder than you think it to be, because it isn't clear if that's going to be an infinite loop or not. The only way really of knowing if it's an infinite loop or not is trying it out.
Running it.
And see what happens, yes. Which isn't very satisfactory, obviously. So algorithms really do have at least an implied output of all the time. So when we're looking at algorithms, we're trying to do, I guess, two things. We want to know if it actually does the right thing. We're trying to code it up for solve some sort of problem. We want to does it actually solve the problem or not? So we're looking at minimal spanning tree, so Prim's algorithm, for example. Someone asked yesterday, does it actually give you a minimal spanning tree or not? That's really what the boil down is. If it doesn't, then it's not a very good algorithm. No, it does, and you actually have to try to prove that if you actually want it. So the person that came up with Prim's algorithm in the first place had to prove that it actually did work. I've just told you it does. I haven't tried to prove it at all. Wikipedia does if you're curious. At least it's a well-known proof. So correctness is important. And so in terms of when you write computer programs yourself, how do you verify correctness?
Usually just got to test it.
Okay, so testing it normally is the way. And even people who did Prim's algorithm, they described an algorithm. When someone tries coding up, you may make mistakes, so testing is always important. But sometimes you might do that in a very formal way, mathematically, or sometimes it's just a bit more pragmatically. You just have to test it out yourself in a more formal way. So that's one thing. So correctness is important, but it's also work out which one's the efficiency. So does it run? What do you mean by? What do I mean by efficiency? So they've got Prim's and Kruskal's algorithms. They both work, so they're both correct minimal spanning tree algorithms. Which one's the most efficient? How would I evaluate which is the most efficient?
Which one gives you the most reliable results? So Kruskal's wasn't it can sometimes result in a disconnected graph, whereas Prim's is
Correctness, I would say one that has the least amount of steps to go through.
Okay, so sometimes you want to talk about correctness as in they are both designed for connected graphs, really. So they both work in connected graphs quite nicely. What happens if the graph is disconnected? Will they fail spectacularly or cleanly? I mean, that's reliable at what you're talking about. That's important, absolutely. So how are they going to handle slightly dodgy cases? Are they still going to do it quite well or not so well? That's one application. That's one thing you want to consider. So how robust it is or reliable. Your other case is how quickly it runs, how many steps it takes. Other things in terms of efficiency is how much memory does it occupy. So some of these algorithms, some of them like the distributed algorithm is colouring nodes in. If you're actually coding that up, it actually has to have a list of all the nodes coloured in. So it actually takes a bit more memory space to do that. That's not that big, currently, a number of nodes it's visited. But sometimes these algorithms have to create lots of extra memory just for all its working space. Is that it? And if you've got an algorithm which uses less, that's better, ideally. And if you start using lots of memory space, then you're going to have to start swapping, and that slows the whole algorithm down too. And so you need to think of not just the time, but space as well. So that sort of is both of them
I want
important.
to know how much memory that Facebook map.
So we're going to so when you're trying to measure how good an algorithm, you need to do both, looking at how all these sort of things. But I guess the two that gets focused on is the time complexity, which is a very fancy way of saying how long it takes to work, and the space complexity, which is pretty much how much memory it uses. Just to illustrate the ideas, we'll just focus on time complexity for this subject. The concept of space complexity is very similar. The way you measure it is very similar. So looking at, pretty much we're going to look at how quickly an algorithm runs or not. So let's look at time complexity. So just want to look at some examples to begin with, and then we'll start looking at how you measure these sort of things. So in Java, just a good example, there's a list interface, which is a way of just storing a bunch of elements in order. So there's an order to it, it's not a set, it's actually a list. They have a few implementations. So one of them is called an array list, which uses an array to store all the numbers. The other one's called a linked list. The one they use in Java is called a doubly linked list. So it's got links going backwards and forwards. I'm just going to show a simpler one, even still, called a singly linked list. So that's just not one of the Java collection classes, but it's a similar idea. So they have a slight generalization of this. So in Java, you've got two choices. You've got an array list or a linked list. Both are quite well coded up, etc. Which one would you pick? Well, let's think through let's do some analysis beforehand to think which one would you pick in a given circumstance. And so let's think of some things we don't understand. So first of all, we need to understand something of how they've implemented it. And they decide that, so if you look up array list, it explains, one sentence how it's implemented. So this is what a single linked list is like. Let's just draw a picture. So you've got the numbers 1, 3 and 4 in a list. So how a single linked list works, it has a head, which is a variable which points to a node object, which would contain the value, so 1 for example, and that would contain a variable called next probably, which would point to another node variable, which would contain the next value, which would then point to the next node, which would then point to the next one. And at the end, what would the last point point to?
Likely null.
Yeah, it's going to be null. So in Java, it actually be the word null except directly. So in C, for example, it'd be 0 probably or something like that. With the simple idea. So it's some sort of null pointer. So that's actually how the data's stored. And so it's a bunch of nodes, and those nodes are basically bits in memory, and they can be all over the place. So you can, so we'll see what some of the good and bad things about this implementation. So that's sort of a singly linked list. That's one idea. So the other way is an array. So an array list, if you want to have 1, 3, 4. So how an array list works is it just grabs a block of memory, probably bigger than what you need to begin with, and then it just chucks in 1, 3 and 4 in those first 3 blocks of memory. And it needs to know how much space it's taken, so you don't want to, the 3 in the end there are basically, although you've grabbed the block so you can use it, you don't really care what the value is in, so you probably need another variable length of 3, just so you know how far you can go along the list before you start going out of bounds. So in an array, all the stuff's there right next to each other. and you can easily work out. So you go, I want to know if I want to go to the second element. So how do you go to the second element in a singly linked list?
You have to go for the first element.
Yeah, sorry. You have to go to the first. You have to go to the head, go to the first one, then go to the next one. So you really have to go to the second element. You have to visit the first one first. For an array, how do you get to the second element?
Just use the index, which is
Yeah.
in this case 1.
So you would know the memory location of the beginning here, which is a number. You add on 1 to it to give the next memory location. That would be immediately location. So you do some arithmetic to work out the location, and then just visit the point. So it's only one memory access, rather than for the linked list, you ever have to visit every node, so there's a few more memory accesses. So, and if you want to visit the last element in the list, so if there was 100 elements in the list, for a single linked list, how quickly would it take to visit the last element in the single linked list? Well, you have to visit every single one first. So to go to the end, you have to start at the beginning and troll all the way through every single element to get to the end. So you have to do 100 memory accesses, so to speak. Whereas for an array, you can access the last one by just doing memory. No, if you know the memory location at the beginning, add on.
Length minus 1.
Yep, 99. That gets you the last value straight away. One memory access. So that's two different implementations. So that's an array list in Java. Pretty much, really much is that bottom one case. In Java, they have links going backwards. And that's cool. And the one when they go backwards and forwards, it's a linked list. That's how Java works. They have links going forwards and backwards, which means you want to go to the very last element. That list is one memory access because it remembers what the last one is. But still going to the middle of a linked list in Java still requires you to iterate all the way through half the list to get to it. With an array, it's immediate access. So to compare these sorts of algorithms and these two different data structures, it's good to think about how many steps it takes to do some of the key algorithms you want to be doing. So you've got to list stuff. You want to do some things, like you want to access points. We've already talked about that. Let's do, so we had linked list, and the array list. So that's just sort of two different implementations. How many steps? So for accessing the ith point element, to access the fifth element really requires us to visit 5 different nodes, essentially. Roughly speaking. So I'm going to be rougher than you might think I'm going to be here. So when you're trying to access that element, there's quite a bit of there's lots of overhead, but I guess the key cost is memory accesses. Let's just go for that one. For the array list, how many memory accesses would we have to do?
Just the one.
Just the one. So in general, you'd have to do, say, I memory accesses. Maybe 1 plus more, depends how you count it, to get to the ith element. So plus 1 don't make much differences here. So the other thing we want to do is look at worst case. So if we've got, so let's suppose we have n elements in the list. So make that 100, 1,000, whatever you want it to be. So the worst case for access for a linked list is if you happen to try to access the last element. That's the worst case. It's about n. Whereas worst case for array, well, it's the same no matter where you are, it's still the same. So you can see for accessing elements, the array list is quicker than a linked list. So what about other ones? What about deleting? What about adding at the end, which is called append? How do you add to the end of a linked list?
You need to insert the element and then update the pointer on
Okay.
the last.
So first of all, you have to find the end of the list. That's the first problem. which means you have to scroll all the way through all the elements. That'll take n steps. And then, as you correctly, then you go, well, no, I've got the last element. I just update the point it's next to. So you can just put in here. You have to scroll all the way through. So you go, now this is the end. How do you know it's the end?
Because you're going to have a null.
Because it'll be its next value will be null. You go, let's make it not null anymore. I'll make up a new node with the value of 7, say, and adjust the pointer from that node into the one I've just created. So essentially, you have to troll through the list, it would be n steps, and then make up a new node, which requires memory accesses and things like that. So say n plus 1, roughly speaking. It does take a bit of work to add at the end. What about for an array list? So that's an array. If you wanted to add 7 at the end of that, how would you do it?
Just get the current length and insert another element at the
Yeah.
end.
So long as you've got some spare capacity at the end of this array here, we can just do one memory access to find where we're supposed to go and chuck the value in there. So as long as you've got spare capacity, very straightforward. Really just takes one memory access to insert the value. Now, if you're out of capacity, say your array you've hit the end of it already, then you're going to have to go away and ask for another big block of memory. Maybe, depending how you implement it, maybe copy all the numbers across to the bigger array. That's going to take a lot more time. So worst case scenario, you might have to do a little resizing, but let's ignore that. So as long as you've got the capacity, which you can often manufacture that case, always have enough capacity, it's nice and quick. So for those sort of cases, it looks like random access and appending, it sort of looks like arrays are better. But what about adding at the beginning? Let's suppose I wanted to add the number 0 to the beginning of this sort of structure I've got here. Throw it out.
You just need to add a new node and then update the head.
Yeah. So pretty much what you do is you just make a new node up, 0 in there, make its next pointer point to the rest of the list I've got, and update the head. So that requires how many different things we did there?
2, 3.
2, 3. Say 3. So made a new node up and adjusted 2 variables essentially. So 2, 3, thereabouts. What about if you wanted to add at the beginning, added 0 into the beginning of my array list?
You need to push all the other elements up 1 and then add a 0 at the front.
So you have to move one at a time, you move the 7 up, and then the 4 up, and then 3 up, and then 1 up, and then you chuck the 0 at the beginning. How many steps does that take to do?
N plus 1.
Okay. So you're going to have to add, you have to shift all the elements you've already got there. That's n elements already, and plus 1 more insertion. So you're adding at the beginning, which is better?
Linked list.
Linked list. So you can see that, just because array list looks better for some operations, it isn't universally better. What about deleting an ith element?
In the linked list, you just remove it and update the pointers again.
Yeah. So it'd be I plus. So you have to access the ith element, and then you have to delete it. So there's a little bit of overhead for deleting it, which is, I don't know, say 2 memory accesses, something like that. You just have to update a pointer really. It's not just one. So deleting it really just requires finding the point and then updating one pointer. That's all it really does. And so worst case would be n plus 1. We are making the last pointer to null. What about deleting ith element for an array? So if I wanted to delete the 3 there, for example,
Move it and then you shuffle the 4 and 7 down 1.
So you have to go and find the element. That's easy. And delete it, and then you shuffle everything down. So the issue is all about the shuffling down. So,
however many are after it.
yeah, so n minus I effectively is what you're is a little shuffling down cost. So worst case, what's the worst case? Yeah, if you delete the first element, that's when the real worst case is. So you can see deleting a random element is, can be costly either way. Depends where you're deleting, I guess. But if you want to delete just from the beginning all the time, so say you delete first element, that's 1, worst case is 1, and so delete, if you're going to add and delete from the beginning all the time, the linked list is much more efficient than an array list is.
But deleting the last, the array list is always fastest.
Yes. So adding and deleting to the end of an array is quicker on the other hand. So which is the better data structure? That's correct. Depends what you're doing. So some application might have as a stack. So how a stack works is you want to basically you want to put a bunch of elements on there. So you're just kind of piling up elements on the top, and then when you want to pull them off again, you just want to take them off from the top. So last in is first out, or first in, last out. So what a data structure would you use to implement a stack? Which would you choose of these, or are these?
Probably the linked list.
Yeah. So in Java, the linked list has the interface of a stack, as a matter of fact. So the standard words for stacking is popping and pushing, and they're actually the interface for the linked list for that very reason. And so you basically, how you run the stack for a linked list is you basically push it onto the front and pop it from the front. So you're just adding and deleting from the front of that list. And it's pretty quick, because you really are just utilising the strength there of that linked list. Whereas if you've got a bunch of numbers, if you want to sort the numbers out in place, an array is much easier to do that with, because you want to have lots of random access. So common sorting techniques is pretty much I look through the list, find the maximum value at some point, somehow or other, either recursively or directly, find it and then move it to the end, shuffle everything down or whatever it might be. Or just swap elements is the quickest way actually. So I know that's the maximum, I'll just swap it to the end. And so you need to have lots of easily be able to swap elements no matter where you are. That's random, lots of random access. And things like an array is much better than that, than a linked list. Because linked list really requires trolling through the whole list every time you want to do a swap. So it does depend on the application, and knowing a little bit of that helps you when you're trying to decoding which data structure to pick. Now they're nice to be well coded in Java, some of them can be thread safe, etc. Neither of these ones that are really. But you can, so it is good to understand the implementation a bit, and just understanding the time complexity, just the cost for each of these is also important. Which takes more memory up? The linked list, probably because it has because it uses a class to represent each bit of memory. There's going to be overhead for that. When array would be just a block of memory, I'm sure Java does it more efficiently. There's not much difference,
in
perhaps.
Java, you can't actually change the size of an array after it's created. You need to create a new one and copy the data over. So you've got a certain amount of memory, and when you create it, it just initializes everything is the default value for that.
So if you do an array list, if you just create an array list with just the default constructor, it makes it of capacity size 10. That's its default value.
Yeah, that's an array list.
Yeah, and you can make it bigger, and you go, look, I know I'm going to get about 100 elements. I'll make that capacity.
Array lists are variable. You can push data in as much as you want. It doesn't matter. But arrays on their own.
Yeah. And again, so I mean, so array list is good that it can update the size if you need to. And other things like that. But no, it just how it deal with an array directly often is just good enough. If you know exactly the size, you can do it quicker. So, but it's good to evaluate. So you can see that things that we need to do is you do need to think about what you are trying to do with it. So you can just because some things look good doesn't mean that it's all universally good. So you have to think about the particular thing you're trying to do with something is important. Also, as you can see, a key thing we want to do is we want to look at the worst case. Okay.
Click on the page at the top. Nope.
So a key thing is we want to look at the worst case scenario is often a key way. So sometimes, deleting the last element of an array is quick, but deleting other elements gets slower because you have to all the shuffling down. And looking at the worst case is often what we have to do, or maybe the average case sometimes that as well. So these are key things when trying to analyse how many steps something takes to do. Okay. Yeah, so let's do another comparison. This is between different sorting algorithms. Again, just try to understand them a bit. And again, just try looking at ways to analyse these sorts of situations. So something else I should say about that case is there's lots of things that happen when you're doing those sort of programs in Java. Like there has to be, to access memory in an array, you actually have to add some numbers together. Or you don't directly, the computer does for you, to access the memory. So it does an addition and a memory access. And so there's lots of things going on, and depending on how it's and how the underlying computer's working, it can take something. So memory access could be a lot slower than adding two numbers in normally they are. So I just did count of the slower things, but you can see that you often want to try to get a high level counting procedure, otherwise it just gets too complicated. And you go, look, how can I justify comparing things that way? So we needed some sort of notation which can handle that bit more flexible way of counting. Because I haven't done it very accurately, really. But normally but to give a rough comparison, that's always sufficient. Okay, so we'll come back to that issue in a second. So the last thing we'll do is just compare two different algorithms. Look at two, so a selection sort and just a divide by quicker sort. So a selection sort, this one was mentioned in the first assignment, and I think it's in one of the other assignments too. So pretty much you've got a list of values and you're trying to create a new list. So a smart way of doing this is to do it all in place in an array, but let's just, we won't do it. We won't do it the smart way yet. So basically, you look at the old value of list, you're just trying to find the maximum at any point in time. To find the maximum value, get the maximum, then you pull it out and chuck it in your new list. And then you repeat. So you've got a shrunken list now, find its maximum value, pull it out, chuck it in my new list, and keep going. The list gets smaller and smaller, and eventually finding max is very easy because there's one element left. Pull it out, and that's done. How many steps does that take to do? So there's different ways of counting. In the first assignment, we counted a number of comparisons that would take. Just to be different, to get a slightly different number, basically think when you have to do the assignment. Let's use memory accesses. So we have to work out the maximum value. So we start with a list of size n. How many memory accesses would we have to do to find the maximum value of that list of size n? Yeah, that's right. So you pull one out on the maximum. You probably remember the value as you're going through, so you've already pulled it out. So next time you have to find, then you've got a shorter list. How many different memory accesses would you require to find the maximum of our shorter list?
At -1.
In -1. Next time.
-2.
Etc. What will be the last case?
N minus N plus 1.
Or 1 for short, I guess. So the last time would be, there's a list of size 1, finding the maximum, well you know what the maximum is already, just pull it out, etc. Now I've ignored overhead of actually have to create the new list, which is non-trivial, but that's a rough idea. I want to know how bad that is. And I could work the sum out, so if you know a bit about sum. So commonly though is we want to know just how it grows. So if it's a small list, if for size 3, adding those numbers up doesn't give a very big number. A computer can do it, no worries. But if you start getting bigger and bigger lists, that can start growing a bit. And so it's easier to understand just in terms of how this thing grows rather than the actual value. So in that case, it's easiest to look at a bound for it. So how big it gets. So n is less than or equal to n. N minus 1 is less than n. Believe with that. So 3 is less than 4, for example. And n minus 2 is less than n as well. And 1 is less than n, like you've got a list of least size n. So all of those numbers are less than n. If you add them all up, what do you get? How many n's do we have there?
N amount.
N amount. So it'll be n times by n, which is n squared. So just a rough way of doing it, that the time complexity is less than or equal to n squared. Now that's a very rough way of counting how many steps it takes to do, of course, but that's a rough way of doing it. So that's and so later on, we'll say that this algorithm has time complexity of big O n squared. I can write it down. That's how we do it later on. So, and that's sort of the reason why we're doing this sort of approach, but I'll explain that next week. So another sort of approach is, which is a sort of divide and conquer sort. So in your assignment, it mentions the merge sort. This is just an example. This is just a basic idea of how these sort of things work. A heap sort is more how this is programmed up directly. Basically, how it works is we need to have a way of inserting a point into a new list. So we've got, as the algorithm goes along, we've built up already a sorted list. We want to add one more element in, effectively. So how it works is it goes to the middle position of the list. If you happen to be equal to that middle position, fantastic, I'll just add it right there in the middle. Done. If it's not equal to that value, if it's less than it, I know it's in the bottom half of the list. If it's greater, it's in the top half of the list. And so I know what half it's in order to quick straight away. And then just focus on just the half I want to. And then repeat. So I know it's in the bottom half, I go to the middle of the bottom half, so a quarter point, and then can do a comparison, work out if it's which quarter it's in, and keep going from that way. So, so we had, say, I elements in my sorted list. How many different divide? So if you're trying to insert one element in that list, please divide and conquer method. How many different comparisons do you have to do? Let's make it a bit easier. Let's just do, say, 2 to the power of I. It's a bit easier to count. So first of all, you check. You go to the halfway point. So divide by 2. That'll be the halfway point. Do a check. Once you do that check, you'd either, most of the time, you're probably not going to get exactly equal. So worst case, you'd either be bottom half or top half. So you'd have to divide that by 2. So that would be that's the size of the next little list you're looking at. Again, every single time when you do the comparison, worst case is you'd have to keep dividing the number by 2. And you keep going down until you keep dividing and you've got one thing left. And you go, well, I know where it is, I just insert either before or after that point, and that's it. I know exactly where I need to insert at that point in time. So that's the number of times you have to insert. So that would be 1, 2, 3, 4. That would be I comparisons you have to do effectively. Or I memory accesses, the same sort of thing. So you're basically accessing I different points. So if this was number k, then I is equal to log base 2 of k. So the relationship between those two things is the opposite of a powers logarithm. Now, I presume some of you guys don't quite understand that. It's true, just take it for granted. That's just the definition of a logarithm. If you don't know what logarithms are, it's a button in your calculator. So I'll say more about logarithms, but that's the short answer for the moment. It's just some way of solving that sort of power situation. So the way of making sort of sorting algorithm pretty much is just pulling out a random element, first element for example, put it in your list, pull out another element, and then use this divide and conquer sort, divide and conquer insert just to add the new element in. So the first time you only got one element to chuck in. The next time it'd be log base 2 of 2. Next one would be log base 2 of 3 to add into the list. So it's always keeping log base 2 of whatever the numbers are. Up to the last time when you're trying to chuck in the last point into a list, it's log base 2 in minus 1. It's anything you've got in my sort of list. And same trick as you did before, each of these can be considered less than log base 2 of n. Each of those things are less than or equal to that. And just like before, we still had any of n of them. So a sort of really worse, so an overcount for how many steps it takes, it'd be n log n. So this sort of sort later on, we'll say has time complexity of n log n.
That's really just one thing. What are the base 2? What happened there?
You don't need to write it down, which I'll explain like next week.
I'll take your word for it.
Yeah, so Berg, if he goes to